Right, okay, right. Okay, ladies and gentlemen, if you'd like to get yourself settled down, because of the way we're running this room back to back, my talk has already started. And I haven't got much to cover, but we'll do what we can. Yes, so that's everything that makes up the GNU tool chain. I'm going to go through some of these slides very fast because it's reference material. It's so you can go back and look at the video afterwards if you want to check something. This is only going to look at GCC, so I'm not going to worry about the assembler or any of the other stuff. I'm just going to look at the compiler and how you add something to a new chip. So how you get the back end up and running, where you can get more information, how you can, what the key things you need to do are. And what I hope is at the end you won't be able to write a new compiler, but you'll know where to get started. So first of all, source of information. There's loads of theory behind compilers. There's an excellent beginner's textbook there. You can still buy it second hand. I believe someone bought one for a penny on Amazon second hand. So, and I've been I haven't used the second one, but it was strongly recommended by someone else there. And this is the Bible. If you've got a lot of money, you can buy the one on the left. If you haven't got so much, the one on the right is still widely available. But this is what we're going to worry about today, the GCC internals manual. Everything you need to know is there. Some of it's out of date, but it's generally a pretty good document. And it's online, so you can just go and get that. So, we've got a new chip. Our new chip, this is an entirely fictional architecture. It's taken from my textbook that I showed earlier. And it's a simple byte stream architecture used for just as a target you can compile to for demonstrating how to write a compiler. So we've got arithmetic, we've got logic, we've got shifts, we've got the ability to store and load, and we've got some branching and a branch and link so we can do subroutine calls. And there's all the details of it, but we'll come back to that. So getting started. First of all, you need GCC, so you can clone it, and there's a mirror on GitHub as well. You've seen this from Dave. Here's the structure, and the bit we're going to be concerned about is within the GCC, primarily the config, because that's where you put the configuration for the new back-end architecture. So we're going to, there's one for RISC-V AVIO, there's dozens of them there. We're going to add one for VAM. So if you were to look in RISC-V, you'd find these 4 key files. There's loads more in the RISC-V directory, but you have a .h file, which is where you define a lot of parameters that says what my backend looks like. You know, how big's a char, how big's an int, and so forth. You have RISC-C, which is where you put C code, and it's really helper code to get you off the ground. You need hardly anything in .c to get started. The big one, and where we'll spend quite a lot of time, is the machine description. It's the thing that describes what your architecture looks like. And GCC will then pick that up and use that to be able to compile to your target. Okay? And it's written nominally in a dialect of Lisp called Scheme. Okay? And lastly, there's a file called .opt, and you don't actually even have to have .opt, but it's where you've got target-specific options. And our architecture, we're going to give it an option that says you can have soft multiplication where you do multiplication in software, or you can have hard multiplication where you actually generate multiplication instructions. So, first of all, we need to see how do we configure GCC for my new target. Well, first of all, we actually need to go into the whole autoconf system and actually add it in there. So at the top level in the repository, you'll find a file called config.sub. Now, that is actually pulled in from a separate project. Okay, so if you're doing this properly, you would go to the project listed there and you'd make your change there. But I'm just going to hack it today, and I'm just going to add a line in the, if you look in there, you say case $CPU, where all the CPUs are there, and I'm just going to add VAM, our architecture. So now the automake system will understand about VAM. And then inside the GCC subdirectory, so the GCC proper subdirectory, there's config.gcc. And that's where you put all the GCC specific configurations. Okay? Now, our full name of our architecture is probably, our compiler will be vam-unknown-elf-gcc, because we'll put the full triple in front. So vam whatever you like, elf will match that. So if you go and say I want to configure for that target, what do I define? And there's a whole load of variables you can set to tell your target what goes in there. The thing is, you don't really need to put anything, because it'll know there'll be if my target's VAM, you must have a vam.c, a vam.h, a vam.cc, a vam.h, and a vam.md, and maybe a vam.opt. I'm going to say, actually, I want one other, because this is bare metal. I'm going to take the standard LFOS file for bare metal operating system file and add it to that, and that's the target machine list of files that make up that architecture. So that is all I need to do to make GCC nomad. And now I can say, go and configure GCC, and this time you'll see it's a bit like Dave did, but this time my target is going to be vam-unknown-elf, and it will configure for that. I'm going to do, I'm going to put it in when we've finished it, it'll get loaded in, it'll get installed in optvam. We'll do it without headers just to keep it simple. We'll just do the C language and, as Dave said earlier, disable the bootstrap. Just a stage one, which is on a plain C compiler. And there's loads more options there, and we'll come back to that later. And then I can just say make all -gcc, and lots happens, and then it will complain and say, but I can't find vam.md, the machine description. Okay, because I didn't actually create a machine description. I just told it here's my machine. So we're going to have to do something about that. So let's start adding those files in. Let's start with the header file. And so let's create our configuration directory. So we'll go into the source directory, we'll come out of our build directory, go into the source directory, create a subdirectory within GCC config for vam, for our architecture, and I'm just going to create empty files, vam.cc, vam.h, vam.md, and vam.opt. Come back into our build directory, make all GCC again, lots more happens, and then I get an error message. It says, in somewhere deep inside the GCC world, I haven't found a definition of first pseudo register, and maybe you meant first virtual register. And that's actually one of the variables that I have to define in .h. So in .h, there's a whole load of macros I've got to define that I will need for that. Okay? So so in vam.h, we've got some things. You define target CPU, but those are the built-ins I want to appear. You know that when you compile for a particular architecture GCC, there are some predefined macros there, including one that tells you what your architecture is. So we want _vam in capitals and lowercase. Actually defined, so if you're writing code, you can put #ifdef vam, ifdef __ vam, and put your vam specific code there. And there's a couple of asserts there. I'll assert the CPU's vam and the machine is vam. Okay. Where does it go? What goes in the header file? There's a whole section on this on the internals manual. You'll be here till 2057 if you try and put all of those in. Easy approach, do what we all do, is copy an existing architecture and hack it around for you. OpenRISC is a really good one. It's quite small, and Stafford Horn knows what he's doing. So it's a good starting point, and it's what I used. Okay? And, as I say, associated implementation goes in vam.cc. And it's things like data storage, data types, register model, the ABI implementation, all the constants that will define that. Okay? So here we are. Here's my storage layout. You know, all the number of bits that go in everything, what boundaries I'm aligning on, the sizes of all my data types, what the ABI looks like. So I've got a comment to say what it does, and then I define the first pseudo register. So I've got a total of 33 real registers, and then anything else will be a pseudo register. And I'm not going to go into pseudo registers today, because I've got my 32 real registers, general registers, and I've got my status register. I don't have the program counter as a register because it's not actually exposed in my architecture. I have no way of treating it as a real register. It's just something behind the scenes. And I've got names for all my registers, and some of those have fixed purposes. So R0 is always tied to 0. R1 is the stack pointer. So I've got an array telling me which of those have got predefined uses, and the last one is the status register. That's got a predefined use. And then what are good ways to allocate this? So when GCC needs to use a register, what's a good one to choose so I don't actually end up choosing one I have to then worry about restoring and everything? And so I can give that in a priority order of what order do I want you to allocate registers in. We talk about register classes. Now this is very simple because we haven't got many registers. Normally you would separate out your integer registers from your floating point registers, and then you can tell GCC to do different things depending whether you're doing floating point or integer. In our case it's only an integer machine anyway, so we've just got general regs, and we've got one class for the status register, which is the flag regs. You always have a no reg class, which is no registers, and an all reg class, which is all registers, and you define the last thing in that enum, because it tells you the size of the enum, is lim reg classes. Okay, and then from that we can define a macro called nreg classes, and we can define the names of these, which are just the text strings. And lastly then we say for each of those classes we're going to have to give you 33 bits to tell you for each of those classes which bits are there. So for the no reg, none of them are set. For the general registers, all the bits are except the 33rd bit, and it's the bottom low bits on the left and the top low bits on the right, and then the status register is register 33, so it just has one bit set in the other bit there, and then all reg has all the bits set. Okay, and you've got a macro to tell you which you're given a register number, which register class are you in, and there's loads more in there, and you can read through it there and see what happens. So we say make all GCC, and even more happens, and then it complains that it can't see SP reg num. Now you think, didn't I define a stack pointer? I did, but I decided something else, because the point is this is not SP reg num as known by a header, this is SP reg num from the machine description. Okay, so some of these things are actually not defined in the header, they're defined in the machine description. So if we look how code generation works in GCC, it's generic. Okay, it's a pattern matching compiler. It looks for patterns and replaces them by new patterns. Okay, it's how it does code generation. It's actually also how it does optimization. And what we have to do is give it all these pattern templates in order to be generated, and that is what the machine description is. And actually, when we come to optimization, replacing patterns by better patterns is what you do. So we heard from Dave the different types. You've got generic, then Gimple, then RTL, and we're really worrying about how you get down to the RTL level. Okay. Side note here, GCC has its own name for type systems, so they're everything from quarter integer 8 bits up to double integer and tetra integer and double float with, and so they're known as QI or HI and so forth. And you can have unsigned variants of those. Those will come all the way through. So when you see those, they're just sizes of things. So how do you get Gimple to go down to RTL? Okay, which you can then code generate from. Okay, we provide a set of standard patterns. Okay, and all you're going to do in the machine description is tell him, given add QI3, that's add quarter integer, 3 arguments, 2 source arguments and destination, and they're mostly free address code like that. So add 2 quarter integer and so forth. There's a whole set of these to define. You define all those, okay, and then GCC has all the patterns, and it will generate code for your machine. Okay, so quite a lot of these have to be defined, but some of them don't need it. You know, you don't need atomic and vector patterns if you've not got if you haven't got atomic ops, or if you're not a vector machine. Okay, so as I say, when we build the compiler, it's parsed, and all that scheme description of these patterns will be turned into C, which is then then compiled and put in your GCC compiler. And there's a whole huge chapter on this in the internals manual, machine descriptions. But we will do the same thing, is we will copy an existing machine description and hack it. So we'll take OR1K again. Okay, so let's have a look. I want to just describe machine descriptions. I'm taking these from risc5.md just because I want to show a lot of ideas here quickly, and they're richer in the risc5 one than in my simple one. Okay, so at the heart of it is define instant. Define instant, which is the semantics of a pattern this architecture supports. The name can be anything, but obviously we're worried about the predefined ones, and add SI3 is one of them. Okay, and that's how GCC can lower RTL using that name. Okay. So the first thing you see is match operand. That's telling you how to match the first operand and then the second operand. And you see there's match operand, size of it, single integer, number of that operand. So we've got 0, 1 and 2, and then a bit about what it is. Okay, so register operand says I can be any register. It's an allow or deny gating function. Okay, and you can write your own predicates as well, but there's a whole load of standard ones. Okay. And then we have constraints on that. Now, the constraint is not much here. Equals R, comma R. And that's saying I'm giving you two scenarios. And they actually both happen to be R in this case, but we'll explain why that is. So, and the equals means I'm writing to it. So, I'm either writing to a register or I'm writing to a register. Okay? Now, the reason that matters is these pairs go together. So, the second operand is a register. The third the first operand, and then operand 2 is register or I for immediate. And you have to read those as though they're in columns. So, we're looking at one scenario where first operand is a writable register, and the other two operands are registers. And we're looking at the second scenario where the destination is a register, the first operand is a register, but the second operand is an integer. So if you think of them in columns, that's how to think of them. Okay? And yeah, so the next line, which is just empty here, that's often for a global predicate. Okay? And that could be where you put one of your flags. So you may have to find a predicate like, is this soft multiplication, in which case I can't generate a multiply. Okay? And just empty means true, just always do this. And then the code generation template, it's just a C fragment. And in this case, so we say if it's a 64-bit architecture, then generate the string, add word, blah, blah, blah. If it's a 32-bit architecture, then it's just a generic add instruction. Okay? And the percent elements there, percent 0, percent 1, percent 2, refer to operand 0, operand 1, operand 2. Okay? And at the end, you can add some attributes. We're not going to worry about attributes in VAM. Attributes are useful because they're a way of tagging the instance, and sometimes you can have code generation options and optimizations that can take advantage of them. Okay? So let's look at what we did for VAM. First of all, you define some constants, and that's where SP_regnum, the numbers of the key registers, is defined. Okay? And then we've got a very simple instance. It's called noop, and it doesn't have anything to match. Really, it's just constant 0, and it generates the text string it generates for code generation is just nop. Here's a more complicated one, add SI3. You've seen that bit before. We've only got one sort of add. Okay? The first operand is a destination register. The second operand is a register. And because VAM is a two-address machine, okay, so add A, B means add A to B and put the result in B, we actually have to say the destination, you see I've constrained it to be 0. That means it's got to be the same as operand 0, which is the destination. Okay? And I've got the same for sub I, and the template to generate the code. Okay? So, the standard names, the standard MD patterns, machine descriptions, and output statement, how you do the assembly language templates, and you've got some useful files in there, and I say the OpenRISC one is a good example that's pretty simple. Okay? So, what about the option file, vam.opt? There's the whole spec on this, and we're going to allow it to have hard division, soft division, whether or not you generate multiply and divide instructions. And they have a fairly simple pattern of displaying what it is and a bit of descriptive text. Okay? Okay, putting it all together. So we do make all GCC and almost everything, almost everything happens, and away it goes, and it blew up. Cannot stat temp emit 10.cc. No, I have no idea what this means. It's deep in the bowels. It's gen emit. So what do we do about this? I asked for help, and so thank you to Maciej Rzycki, who came up and said, "There's a trick. You can tell it to emit fewer partitions. It might be a bug." And so I tried with emitting 5 partitions, and it all worked fine. Okay, and actually I ended up with a GCC. Because XGCC is what the GCC within the build tree is called, and it ran its self-test. It said, let's check if the compiler's any good. And then I got an internal compiler error, because I haven't actually finished doing my compiler. So vam.md is missing some patterns, and it's essentially blown up because it couldn't work out how to find a pattern to get the code down there for one of the test cases. But I do actually have a working compiler. Well, I have a working compiler in the sense I've got a compiler I can run. It will crash whenever it compiles things, but that's actually quite an achievement. So now I need to just debug it, okay? But I have actually got a GCC built. So Dave covered this, how to dump stuff. Yeah, so you didn't know, you just mentioned it. So you can dump all the different intermediate codes, but what Dave did cover was the wrapper option, and the wrapper option is your friend. That's where you can go inside. We've talked about the wrapper option and how it puts things here. Actually, you can do the same sort of thing as you can do GDB args, and then I just copied that error message I got with the internal compiler error, and now I can run under there, and I can run it, and I can generate my internal compiler error under GDB. But I now have the ability now to do to debug it. Okay.
You can type make self-test-GDB and it will run the self-test.
Even better. So there we are. And this is why we work as a community, because we are. So make self-test-GDB will do all this magic for you. Okay. So there was a bit of smoke and mirrors in there. I created a minimal vam.cc. Guess what I copied it from? There was a bug in vam.op.uls. I had to hand create that and hack around that, and that I think is a bug. I had to create vam-common.cc, and I'm not quite sure why I had to do that, but everyone seems to do it except OpenRisk. And I had to do it to make it, and I just took the template one and used it. I added vam to the documentation. That's a good thing. I also compiled with enable maintainer mode, which is used to regenerate some files. That was when I was trying to fix the URLs problem. I'm not sure I actually needed to do that, okay? But that's what I did to get there. So what next? And the reason this is rather rushed is it's part of our 3-month graduate training course. This stuff was put together by my colleague Maxim Blinov a few years ago. It's a 5-day part of the course, for 8 hours a day with exercises, and so I've compressed it into 25 minutes. But hopefully it gives you just a little bit of a touch on how you can get started, and there's enough hooks in there that you'll get off the ground. And if you get stuck, ask for help. We're a friendly bunch. I have an ambition. One day I'm going to create a full public tutorial on GCC. That's probably my retirement project. But in the meantime, everything I've just shown you is on GitHub. Thank you. Okay, I've got 2 minutes for questions. Yeah.
Are there any ready-made CPUs that are a bit weird, like big TARs that we can use and play around for fun?
Yeah. So the question is, are there any ready-made ones? There are loads. I mean, there are, what, 50 or 60 backends for GCC, and some of them are really weird, and some of them very normal. I would look at OpenRisk because it's relatively recently done, it's well done, and it's quite small. Yeah.
I'm interested in working on the PowerISA backend because
Great.
it needs more work to add scalable vectors in C. We have had notice, and now we have to work on GCC.
Excellent. So the comment was about working on PowerISA and adding the scalable vector functionality into the back end. Please join in, ask for help. Scalable vectors are the flavour of the month at the moment. So.
You said that we have to add the architecture-specific stuff in the machine description. I was wondering if there is a minimum set of Turing to complete, that you say that you do the assignment, the addition, and this.
Yes, question for the audience. Then we'll start. The question is, yeah, our time's up. What is the minimum set in the patterns? I don't know, but if someone could tell me, I couldn't find that. Thank you.
Thank you, gentlemen.